Okay, so welcome again. Today we're going to talk about machine learning terms. There are specific terms that you have to use correctly, like deep learning and machine learning, and what is the difference. So all these terms and how they relate to each other, this is one thing we will be talking about. And then we will also talk about what genetic computing is and how it works, what the idea behind it is, what the principle is. We will learn a little bit about evolutionary theory that we need for this. Okay, so first to the machine learning terminology. Machine learning and deep learning. Machine learning generally is called every kind of computing system that is able to learn, right? This is what machine learning is. And this can include symbolic systems, right? Symbolic systems also can learn. You can imagine a Prolog program that has the ability to learn new things in a symbolic way, right? You enter some new facts into the database, for example. You say that Tweety is a penguin. This is a symbolic fact, and this symbolic fact, when it goes into the database and is learned by the system, then becomes fact that has been learned, right? So this is a kind of machine learning that is symbolic. But it also includes neural networks, it also includes reinforcement learning and so on, right? So these are other types of machine learning. So every method that makes a program learn something is machine learning in general. But then we also have deep learning, which is sometimes used synonymously, but it's really something different, because deep learning is a type of machine learning that is based on deep artificial neural networks, right? You remember what these are, we talked about them before. So when you have a deep neural network and this is learning, then you call this deep learning. And deep neural networks now, you remember, are artificial neural networks with more than 3 layers. Then we call them deep. So typically there should be 10 or more, right? If you have only a few layers, then it's not called a deep neural network. These are particularly good at visual recognition tasks, but they can also be used for other applications, right? So image recognition, sound, speech recognition, you speak something and it appears on the screen. But what Google Voice typing, for example, does. So these are applications of deep neural networks. Okay? And now machine learning generally involves 3 different kinds of tasks. And these 3 things are the most common applications of machine learning. So the first one is regression, the second is classification, and the third is clustering. And some of these run in a supervised mode, are called, supervised learning, and some are called unsupervised learning. And the difference we will see in a moment, the difference is whether there is a teacher present who tells the system what the right answers are or not. If there is no such teacher who defines what the right answer is, then we call this unsupervised learning, otherwise we call it supervised learning. So regression now means to put a line or a curve through a collection of data points so that one is able to predict where new data points will fall, right? If you look at this diagram here, we have weight on the left side, on the vertical axis, we have the right at the bottom, and we have a line that connects these points, that is put through these points, and this line allows us to predict when new points will fall. The whole point of such a diagram is to say that I expect that new points will fall onto the line. It doesn't matter that I have a few points that don't fit, right? We have one point at around 160 height, which goes up to a weight of 80 kilograms. This is an outlier, right? This doesn't mean that I cannot draw my line, right? I can still draw my line, and I just ignore this outlying piece of data. So this is called regression, right? And this is one thing that AI program might want to do. It doesn't need to be a straight line, obviously. Here's another example. from the internet somewhere, are these graphics. And here now we want to understand the relationship between two variables. This is true of every regression, so that you can predict the value of one if the other is known, right? And the regression curve can be something like this. It can be a very complex kind of relationship between these variables. So what are some examples of regression? It's perhaps easier when we talk about applications of AI to think of examples. So for example, from a list of house features, let's say you want to buy a house, or you look at the market for housing. From a list of house features, you say living area, location, the age of the house, the number of rooms. You want to predict the sales price for that house. So now this gives you a multidimensional kind of regression, because you don't have only two variables, you have lots of different variables. But this is not a problem, right? The thing works in the same way. Or from a list of tumor features in medicine, in cancer treatment, you have the type of tumor, you have the stage of development, you have the organs that are affected, and from this you predict the probability of a successful treatment, right? This is another kind of regression. From a list of student features, for example, the grades in secondary school, or the frequency of Facebook updates, the list of hobbies and interests, the number of languages that the student speaks, the participation in student societies, the grades in the midterm exam, you try to predict the expected final grade in this course. Well, this is also possible. And a final example from a video feed. From a camera in front of a car, you predict where the other cars will be 1 second later. This is something a self-driving car would be doing, right? So these are all regression. You have a big amount of values, and you try to find some regularity so that when you know one value, you can predict the other. Now, the second type of AI machine learning prediction is a classification. The classification is different from the regression, because the desired output of the network now is not a continuous number on a axis, but it is one of n. N is any number, right? One of a number of different bins into which the output will fall, right? Or the input will fall, and the output is the bin. Okay? So the point is to classify the input as being a particular one out of n kinds of things. You see an image of a thing and you say it's a bird. You see another image, you say it's a car. You see another image, you say it's a coffee cup. So this is a classification task, and you can distinguish, of course, binary from multiple class classification. If your question is it a bird, yes or no, then you're doing a binary classification. If you're asking what thing is this thing in the picture, and you have the options bird, car, or coffee cup, then you have a multiple class classification, because your output is not only binary, yes or no, but your output is a continuous, not continuous, is a number of classes into which something can fall. So, for example, from a picture of an animal, find out if it is a cat or a dog. Okay? From a picture of a person, find out if it is a man or a woman. From a person's given name, find out whether it's a man or a woman. This would have lots of practical use if this was possible, because you have all these Mr. and Mrs. Prefixes in office software, for example, when you write a letter, dear Mr. something. If it was possible for the machine to predict whether this is a Mr. or a Mrs. just looking at the name, this would save a lot of time for people who have to type these addresses. But obviously this is not easily possible, right? Because you know that there are ambiguous names, and you cannot always tell from the name what it is. Or sorry, I have a cold. So to recognize the objects in a video image is another thing, right? Another example of classification. Recognize what a self-driving car sees on the street. In front of it, the car sees something, a box, and now the car has to decide, is it a another car? Is it a dog? Is it a human? Is it an obstacle? Is it a box that fell off from a truck? Do I have to go around it? Or is it perhaps only something painted on the floor and I can drive over it, right? So here's an example of a classification from a real world example you find on the internet somewhere. You have this feed, this image that comes from a camera, and your system is recognizing a car in the background, a bicycle, and a dog, and is drawing a bounding box around these objects so that it is easier later to handle them and also to recognize if they are moving, right? This is important. Is the thing stationary or is the thing moving, right? For example, if you are a self-driving car and the dog is stationary, you can carefully drive beside it. If the dog is moving into your path, you want to stop. So this is why it's important to know whether it's moving or not. This is why this bounding box is necessary. What is the difference between classification and regression? The two are similar, right? Both try to predict the future, or they try to predict where this particular piece of input data goes. So what is the difference between them? Can you just try to think about it for a moment? If I say I have a house which has 5 rooms, and it has 2 bathrooms, and it has a balcony, and this thing, what will be the market price for that if it is located in this part of town? And this is an example of regression. And then I have an example of classification. I have an image of a house, and I say this is a cheap house or an expensive house. So what is the difference really between the two? So generally, when we expect a numerical value as an output, we talk of regression. And when you expect one of n discrete bins or tags as output, you talk of classification, right? So this is a kind of continuum, and these things are similar. For example, with a house, right? I could say, let's say I have a house, and I have the number of rooms, and I have the number of bathrooms, and I have the size of it, and the area in the city where it's located, and from this I predict the selling price. So now I have regression. But if I say I have all these data, and from this I predict whether it's a house that costs more than $1 million, or it costs between $500,000 and $1 million, or it costs between 100,000 and 500,000, or it costs between 0 and 100,000. Then now I have bins instead of a continuous number. And so now this becomes not a regression, but a classification task. I classify this house as an expensive, a moderately expensive, or a cheap house. Right? So a very fine-grained classification can be similar to a regression. So if I predict a student's grade, and I say I predict the student's grade in terms of A, B, C, D, E, F, then it's a classification task. Right? A, B, C are discrete bins. If I predict a number between 0 and 100, it's a regression task. But now obviously I can map these things. Every number, percentage corresponds to a letter grade, so that these two are essentially the same kind of operation, right? So the difference between classification and regression is not really that big. It's more that the regression is more a mathematical operation that works on continuous numbers, while classification is a more binary approach. Does it fit in this bin or does it not fit in this bin? Okay, so now clustering, the last thing, is also very interesting in AI. It means the machine will try to find similarities between different data objects by itself. So it is not anymore the case that it learns from all the houses that have particular properties and a particular price to associate these properties with a price, but instead it tries to find similarities by itself. So you don't train it in the same way like you train a classification system. Here you give the system only a collection of data points, and then the system tries to cluster them together to a number of clusters. So For example, you have a data set like a red Toyota and a black cat and a red bird and a blue Tesla and a yellow bird. And now you can yourself, try to find some clusters in these data. Have a look. Right? Obviously, so you can say, I have cars. I have the red Toyota and the blue Tesla is one car. Then I have birds. The red bird and the yellow bird are another cluster. And then I have the black cat, which is its own cluster of one thing. But I could also cluster them differently. I could say I have red things, the Toyota and the bird. I have blue things, which is only the Tesla. I have yellow things, which is the yellow bird, right? So I can cluster them by color. Or I could cluster them, by animal or technological artifact. So then Toyota and Tesla would be one cluster, technological artifact. But cats and birds together would be the other cluster, animals. So there are many different ways of clustering things. And sometimes it's nice to be able to cluster big amounts of information where a human cannot do it anymore just because it's too big. So when you have here, right? Cars, animals, birds, red things, black things, blue things, yellow things. Some things can belong to multiple clusters, obviously, right? Clusters can overlap. So the point is, in clustering, we don't know in advance which clusters we will find. We just have a bunch of data and try to find some regularities. While the machine processes the data set, it will create new bins or tags as needed. So we don't have from the beginning specified bins where the data has to go, but we just tell the machine, do what you want, find me some regularities in this data set. And therefore clustering is an example of unsupervised learning. I don't provide the machine with the information of where things go, right? I let it put the information wherever it likes so that it forms clusters. And in the end, I look at the clusters that came out. And this is an unsupervised process. So in classification, the bins or tags are given in advance, and the machine has to sort new data into the existing bins, but not create new bins. And because the bins and the example of what goes in them are given during machine training, classification is an example of supervised learning, right? Classification is supervised because I give to the machine the ideal answer together with the data in advance, and it learns to map the data to this ideal answer, to this correct model answer, right? But in clustering, I don't have a model answer. So more generally, in supervised learning, we didn't actually talk why clustering is interesting. So where does clustering happen? Can you briefly think about where we use clustering? Stop the video, think about it for a second. Yeah, obviously clustering is used in online shopping a lot, right? This is the whole thing. Advertising, shopping. So you want to, if you are Amazon, for example, you are a big online retailer, you sell to particular things to particular people. So for example, you sell, dresses to some population of people who buy dresses. But now you want to advertise to these people about other things. Of course, you can advertise other dresses, but there's a limited amount of dresses people will buy, right? So if you only advertise dresses to dress buyers, then you are not using the full potential of these customers, because this customer who just bought a dress might also want to buy something else. But what is a customer likely to buy who just bought a dress? Is he likely to buy an electrical saw or a drill? Or is he more likely to buy, something else? Let's say, I cannot think, a book, a novel, right? Exactly, a novel. So, if you buy a dress, are you more likely to next buy an electrical drill or to buy a novel? And this is something that, of course, we kind of know statistically women read more than men. Women buy more dresses than men. So therefore, somebody who buys a dress is probably a woman. So she will probably buy the novel rather than the drill. On the other hand, if somebody already bought a drill, then perhaps you want to sell him also other things for men, because it's more likely that a man will buy a drill. So then you want to sell them other things for men. And this is a statistical thing. So, you don't need to accept my example as, really representative now. I just made something up. But this is something that the machine can find out by doing this clustering, because the machine would get all the products that people bought and then all the other products that they bought on this site. And because Amazon has the names of all people who buy things, it knows exactly who bought something after buying something else. And then the algorithm can go into these millions of shopping transactions and can try to find clusters and perhaps find totally surprising things. Most people who bought a book by Stephen King next bought a bar of soap for some reason, right? There doesn't need to be any reason that anybody can understand, but if it is true that most people did this thing, then you just can sell them, try to sell them, advertise to them a bar of soap next. So this is the internal logic of this data. It doesn't need to make sense to a human. Perhaps in the Stephen King book, soap plays an important role, or not having soap causes somebody to get an infection, so that people who read this book afterwards, they are scared and they want to buy a bar of soap. Who knows why, right? Again, it's just a silly example now, but the point is that data has its own regularities, right? And an algorithm can discover these regularities even if a human doesn't know why the regularities are there. They don't need to make sense to us. As long as there are regularities, as long as people buy these things, it would be good to sell them these things that they want to buy, right? So in supervised learning now, you have input patterns and a desired output pattern, and the algorithm learns to match the output to the input pattern. The goal is to be able to guess for a new input pattern what the correct output pattern would be. And the process of learning from the training data resembles a teacher supervising the learning process by comparing the expected with the actual output patterns. This is what we said about backpropagation, right? You have the error, the difference between the expected output and the actual output, and this has to be minimized. While in unsupervised learning, there is no expected output. This is the whole point. You don't want to have an expected output because you want to discover new regularities in your data that you didn't know about before. If you knew them already, there wouldn't be much fun in it, right? So in unsupervised learning, you only have input patterns but no corresponding output patterns. So now the goal is to learn more about the data by classifying and analyzing them and to find new regularities. So in unsupervised learning, there is no teacher, there is no model answers. Like in K-clustering is a thing that is a kind of clustering is called K-clustering, which we discuss sometimes in class, but let's skip it now. The algorithm has to find a structure in the data by itself. Okay, so that's it with machine learning. So you should remember, what is machine learning, what is deep learning. Machine learning can be symbolic, right? What are deep neural networks? And you should remember regression, clustering, classification, and the differences between them. And you should also have an idea what we mean when we say supervised learning or when we say unsupervised learning. Okay, so thank you so far. In the next video then we will talk about genetic computing. See you in a moment.